Hi, I'm Tim Berglund with StarTree. I'm here at the Thomas Fogarty Winery in Woodside, California, to tell you all about Apache Pinot 1.1. Now, some fun numbers. Pinot 1.1 had 472 commits, squashed commits, of course, since release 1.0. There were 70 individual committers, including Dependabot. Dependabot needs to be recognized too. 152 bug fixes, that includes refactorings and cleanups and deprecations, and 166 new features. That's counted by pull requests closed. So a lot of work went into this for being just a minor release. Let's look at what's going on in the release. Now, in the query engine enhancements, first of all, there were a number of performance enhancements in the multi-stage query engine. The multi-stage query engine was just official in 1.0, and there are a number of closed issues, closed PRs related to performance improvements. And I'm not going to dig into those individually because frankly, they require a lot of digging to explain. So they're in the release notes, check them out. Let's get into, though, the vector index support. This is brand new in 1.1. Of course, in the post-ChatGPT world, with everybody thinking about AI and incorporating AI into products, everybody needs a vector index. Pinot's no exception. Now, if you don't know what a vector index is, let me give you an idea. Basically, the idea is you have some space of vectors, and you want to know what other vectors are closest to yours. So in 2 dimensions, 2 dimensions is not what we work with in modern vector spaces, but let me show you what that looks like in 2 dimensions. So I got this vector here, and I want to know what other vectors are closest to that. Well, I mean, you could look at it and you could see, okay, those 2 are. To figure that out algorithmically, the naive approach is what? It's just compute the distance to all the other vectors, sort, and pick the top k of those. Now that's a terrible idea because the computational cost of that is going to grow with the number of dimensions times the number of vectors. And so that's something like big O of n squared, or maybe worse. It's not what you want to go for. Now, briefly, what are these vectors? I'm focused here on the Pinot release and not sort of AI broadly. But for example, you could go download a large language model from Hugging Face and using that model, turn a chunk of text into what's called an embedding. Basically, you turn that chunk of text into a vector. And that vector could have many dimensions. It could be 1,000, 2,000, a lot of dimensions that are just created ad hoc as the model is trained. And you're able to convert that thing that you want to keep track of into that vector, which enables you to enhance the results of the pre-trained large language model with your own data set. And that's potentially a data set that's being updated in real time. That would be the whole point of doing this with Pinot, something that needs to be updated constantly and very quickly. So Pinot now supports, with its vector index, the hierarchical navigable small worlds index. And again, that itself is its own 10, 15-minute explanation. Briefly, what we do is we turn that whole vector space into a particular kind of graph that's navigable in an efficient way. So you get now, instead of
big O of d times n, now you get big O of d times log n, which is much better.
That's a huge improvement over the approximately n squared cost that you get from the naive approach. This is how vector indexes typically work. Pinot now supports it. That's great news if you're building, say, a real-time RAG and you've got, some stream that's being consumed and you need to be enhancing the results of your large language model with events in that stream being processed, turned into embeddings in real time. That's a thing that you can do in a performant way now with Pinot. The query would look something like this. You see now we have this vector similarity predicate. Embedding is the column that I'm going to be storing these array values in, and I can have that literal array. That's the vector I'm testing against. I want to see, okay, what other vectors in my table here in the embedding column are close to that, and I'd like the top 5. And that's what we'll get from that query. So again, super great feature. It's becoming commonplace for databases to have this, and Pinot is definitely no exception. Next up, sticky query routing. Now we have to remember, as Pinot is consuming a real-time table, there's a Kafka topic, it's consuming from that topic and updating the table, adding rows to the table as those messages are being consumed. In the presence of replication, which is almost certainly the case, say replication factor of 3, there'll be 3 separate servers consuming each partition. Okay, so say it's partition 3. We'll go with 3 again from some Kafka topic. There'll be 3 servers consuming from that partition. And those 3 servers are going to be asynchronously consuming from that same partition. They're 3 separate consumers. They could be at different offsets at any given moment, which could cause query results to vary depending upon which of those individual servers a particular query is routed to at the time you issue it. So you could see inconsistencies, and that's not great. I think this would benefit from a little bit of animation. So we've got this Kafka topic, and we're just looking at partition 3, that's all. Each one of these 3 servers, 3 replicas of this partition, is consuming from that same topic. So let's go through some animations here. They consume, messages arrive, they fill up the consuming segment gets flushed to a segment on disk, and life goes on. That's great, that process proceeds. Now, the reality at any given instant, though, is that those replicas could be at slightly different offsets, and they will be over time. And so the message available in the consuming segment of the replicas is going to be different. And so if a query lands right now on replica 2 versus replica 3, there's those 2 messages, those 2 rows that exist in replica 2 and don't exist in replica 3 yet. And that's a little messy. So now we have the option of fixing the routing. If we enable sticky routing, all queries of a given table can be pinned to a particular replica. So you just won't see that happen anymore. You get the benefits of replication, which is fault tolerance without this little bit of tiny, message-based eventual consistency. That just isn't a good look. You turn this use fixed replica switch on in the routing section of the table config, and you're good to go. Configurable Lucine analyzer. Okay, so for the text index type, that's when you're using actual embedded Lucine and not the native text index in Pinot. By default, and without option of changing it up till now, all of those have used the standard analyzer in Lucine. Now, to remind you, what the analyzer does is it processes the text and tokenizes it. And the standard analyzer is assuming that it's words, right? So tokens are split by white space and special characters aren't helpful, so it disregards those. It makes all kinds of assumptions that are wonderful assumptions if text is what you're indexing. Well, what if things are a little funny and you got special characters that matter and you still want to use search? Well, now it's possible to specialize a custom analyzer per column, and that looks like this. Now you have the new Lucine analyzer class property of a field configuration. Remember, we're defining an index on a field, so we're modifying the text index to say, don't use the standard analyzer. I'll give you a fully qualified class name of the analyzer I want you to use, and the problem is fixed. You got that flexibility now in text columns, which can be a great thing. Several new approximation algorithms. Now, as any 2-year-old can tell you, counting is hard.
And any adult can tell you counting things is hard if there are lots and lots of things to count and you only want to count unique instances. And so there are tools like HyperLog.
When we're dealing with counting a set with an enormous cardinality, when we don't really have space to fit all those things in memory or come up with a precise count, and it's okay for us to have an approximate count at lower memory footprint and lower computational cost. HyperLog is kind of the traditional standby. Now we have HyperLog++, recommended for cardinalities kind of between 10,000 and 100,000. Super simple to use, it's just there. There's also UltraLog, which is like HyperLog, only even more hyper. It's just another one of these cardinality estimation algorithms. This appears to be an area of active computer science research. There are papers coming out and people saying, hey, like in the case of UltraLog, 28% more space efficient, no penalty in accuracy or performance. Pretty cool. And this works in all the regular places. If I'm ingesting, I can do it as a transformation. I can do it as a query aggregation. I can do it as a segment merge rollup. All those places this plugs in. And it looks exactly like you'd expect it to. You have this distinct count ULL for UltraLog. And there's another maybe a little bit more leading edge one from the Apache Data Sketches project. And that's the CPC estimator, which is like UltraLog, only even more ultra. Again, it's just another approach to the problem, right? So you're going to see different performance, accuracy, memory trade-offs in all these things. And CPC claims to rule the roost in all three categories right now. That would be an interesting thing to test out if you really kind of need to nail performance in this area. But it's good to know that this is an option that you've got, and this is a place where Pinot is trying to keep up with the latest research in this area. There are a couple of Upsert enhancements. And if you don't know how Upserts work in Pinot, don't worry, I'll basically remind you. But there is this somewhat memory-intensive structure called the metadata map that in open source Apache Pinot, that resides on the JVM heap. And anytime you've got something a little bit memory-intensive on the heap, you just need to be careful about what you're keeping around in there. So Upserts apply to real-time tables. When I'm ingesting from a Kafka topic and I get some message from that topic, some event, I'll insert that into my Pinot table, and I might get another event with the same primary key. Upserts allow me to overwrite the previous one. All right, it's a fairly innovative thing for an analytics database to do. Pinot does it very well. Some of those messages can be deletes, right? I can change a value, I can also delete a value. Now, anytime I'm changing a value, I have to keep a pointer in the metadata map to what the current thing is, because I may have written the previous value to a previous segment, which is written to disk and which is immutable. And now I've got this new value, maybe in the consuming segment, maybe in a new segment on disk. And the metadata map needs to tell Pinot, okay, which version of key A or B or C should I be looking at? The metadata map points me to that. That's going to grow over time if there's lots of Upserts. So if there are deletes in there, like let's take a look here. I've got 3 keys in there, A, B, and C. You see they're all represented in the metadata map. And just to refresh your memory, I'll keep consuming, and here's another message comes in from Kafka. The primary key is B and the new value is rocket ship. Well, I put that in my segment and I update the metadata map to point to that new document ID. So now I know, okay, good, that's the proper value of B is rocket ship and not potato. I'm eliding some details here. I'm not showing you what's happening with the consuming segment, just to keep it simple. Work with me. Now we'll consume D. That's red flag. Good. Okay. D is written into the metadata map. A, update A. Good. E. We've got all this writing happening, all this consuming. Now a delete comes in. All right. I want to delete B. And I write that. I say, now in the metadata map, I have sort of a tombstone, a delete marker for key B. So I will not return B from any more queries. Well, how long do I want that hanging around, right? There might be a maximum amount of time after which I'm good saying, we can just forget about it, okay? I've merged all my other segments, I've expired that, it's cleaned up out of there. I don't want it hanging around on my metadata map. I don't want all of those taking up memory. And if I set the deleted keys TTL parameter in the table config to something non-zero, now after that amount of time, the metadata map will be purged of that key showing that B was deleted. So it's just gone. It's completely obliterated from history, and that's a great thing. Another little tweak on the metadata map focused on memory management is out-of-order events. Now, as I am consuming events from a Kafka topic into a real-time stream, there's always a time code, all right? There's going to be a field that indicates the time of the event. That's just a requirement for a real-time table, which lets me know if I see an event that occurred in the past that's older than the most recent thing I've taken for an Upsert. I don't have to go putting that in the metadata map and making my life complex, taking up space. I've effectively already Upserted that. It's an old event. I can just drop it. All right, so now I've got the option to set the drop out of order records parameter in the table config to make that happen. And let me show you that visually just in case it's not clear. We've got this simple table, these 3 keys, they're in a segment, they're in the metadata map, and B comes in. I've got an Upsert on B, that's great news, let's write it. And notice I've got a timestamp on there. Now, you know what? The entries in the metadata map have always been timestamped. I didn't show them in the animation just because it kind of clutters things up a little bit, but they're always timestamped. It's there, just waiting to help. So now we've got that thing that we've written, and we're noting as it goes in there that, okay, this is the 331 version of key B. So when I see another version of B that's 10 in the morning, I can just automatically say, okay, well, 10 is earlier than 3, so forget it. We'll just drop that key altogether and not worry about it, save the hassle in the metadata map, and make our lives simpler. Next and last, we've got kind of an operationally oriented enhancement. Now, there's this funky thing that could happen during rebalance, right? Now, when you're rebalancing a table, you're gonna be copying a lot of segments, moving segments around from the perspective of a given server, potentially adding segments to your local disk and deleting some segments, okay? So for large tables, say 10,000 segments or more, that server is gonna get a bunch of commands from the Helix controller to say, download all these segments that are being rebalanced to you and delete these segments that we don't need anymore. They've been merged, they've expired, something like that, right? Now, it's possible that because the downloads take longer, an internal thread pool gets stuck waiting for those downloads to complete, and the deletes that have been issued, we don't get to those in time, right? And so we're downloading all this new stuff. We would have deleted segments to make space on disk, but we haven't got to it yet because the way the operations get serialized and the way the thread pool got tied up. And well, that's bad because then you run out of disk and that's a pretty catastrophic failure. So as always, I'd like to show you that visually just in case that's not entirely clear. We've got these 3 servers, all right? Now those yellowish segments are segments that are scheduled for deletion, and those peachish kind of segments are gonna be rebalanced because you could see server 3 is really not pulling its load. We need to keep it busy. So Helix will do its thing, send the commands, and server 3 will download that new segment and it'll be removed from server 2. Server 1, same thing, and we're adding this load. Okay, oh, we got to delete, good, we made some space, but let's keep downloading, and now we're in a situation where there were some deletes queued up, but we didn't get to them, disk is full, and that next segment comes in and everything dies. The point of this feature is now we have this low disk mode feature in table config that makes sure the deletes get scheduled first, so we clear up space, and as we're downloading new segments, we don't run out, and that's a good thing. So for a supposedly minor release, there's a lot in there to cover. There's great things you can put into effect right away, cool features you can start experimenting with, like the vector index. And for more details, go to pinot.apache.org. You can see the complete release notes, download, do whatever it is you want to do to get started. And as always, I look forward to seeing what you build.